Hi everyone, welcome back. Today we're doing day 9, recursion in C++, and we'll be exploring a new algorithmic concept called recursion. Recursion is where we implement a function where the implementation makes a recursive call to itself, and that is usually done if the solution to a problem or the solution to an implementation of a function can be broken down such that the solution to that bigger problem can be expressed as a solution to a smaller subproblem. So to be specific, factorial. Factorial is a great example of that. Factorial of 3 can be expressed as 3 multiplied by the result of factorial of 2. Factorial of 2 can be expressed as 2 multiplied by the result of factorial of 1. And factorial of 1 is 1. So in this case, we're able to express the factorial implementation as a recursive call to its own function call. So with that, let's get started. For this task, we're given n, where n is the number to be passed into factorial. And luckily for us in this case, HackerRank implemented the boilerplate for us. So HackerRank used the same tactic of defining a temporary string variable to read in n. This n is then casted into an integer with stoi, and this n is passed into factorial, and the result of factorial is passed into this temporary integer result and printed out to the console here. So similarly in this case, all we have to do is to implement factorial. So with that, let's get started. For every single factorial implementation, there must always be a terminating condition. Every single call to a function takes up memory, and to be specific, we use memory for keeping track of the memory used for the variables in a function, as well as other conditions such as parameters and stuff like that. So what this means is if your recursive function doesn't have a terminating condition, then a recursive call to itself will continue to keep calling itself, and you will eventually run out of memory and end up with an error called stack overflow error. So to prevent that, every single recursive call should have a terminating condition where a given function can terminate and return its result to the parent function that calls itself. So with that, let's get started. In this case, the terminating condition for factorial would be n equals to 1. If n is equals to 1, then the factorial of 1 would just be 1. So we can do if n is equals to 1, return 1. Else, in this case, as we discussed, the result of factorial of n is just return n multiplied by factorial of n minus 1. So this is pretty much the implementation for factorial. So let's run this. This passed. And in this case, this is taking some time. So let's take the chance to explore how this function execution happens under the hood. So let's say if you call factorial of 3, where n is equals to 3, let's keep track of this underlying data structure called the call stack. This call stack manages the memory that is used to keep track of unfinished function calls. And let's start tracing this. When we call factorial of 3, we will put factorial of 3 on the call stack, and that will keep track of all memory used for this factorial function. So factorial of 3 will come into this implementation, and since n is not equals to 1, we will hit line 27 instead. So that will return 3 multiplied by factorial of 2. But before it can return itself, it needs to evaluate factorial of 2 first. So factorial of 3 will evaluate factorial of 2. And factorial of 2 will be placed on the call stack. Factorial of 3 will still remain on the call stack because it cannot return the result until factorial of 2 is evaluated. And now let's look at the logic control flow for factorial of 2. Now n is equals to 2, that means we will hit line 28, and that will be return 2 multiplied by factorial of 1. Now before factorial of 2 can be evaluated, it needs to evaluate factorial of 1. And now currently, let's look at the control flow for factorial of 1. Now n is equals to 1, so factorial of 1 will return 1 back to factorial of 2. So factorial of 1 is popped off the call stack. Factorial of 1 returns 1 back to factorial of 2. Now that is 2 multiplied by 1. Factorial of 2 can terminate and return back 2 to factorial of 3. So now factorial of 2 will return back 2, and now factorial of 3 can return 3 multiplied by 2, returning back 6. So that is how recursion happens under the hood in the control flow. And we were also lucky to see that this passed as well. And that's pretty much it for this question. So in summary, we learned how if a problem can be broken down to the solution to a smaller subproblem, we can implement it with a recursive call to itself. And we also went through how the control flow for a recursive function would go as well. We use a call stack to keep track of memory used for each recursive call to itself, or any function for that matter, and how we can see that when a function calls itself, it cannot return until the result of that recursive call is used. So with that, that's pretty much it for this question. If you found this useful, please give us a like and subscribe, and we will see you in the next video.